Good afternoon to all of you in this session. And yesterday we had a 2-hour session particularly concerning geometry of cutting tool and chip formation mechanism. Following that we had some very fruitful discussion. It was very interesting. So, today we shall move to the section dealing with cutting force followed by that of cutting temperature. Okay. Now, we go to the first slide. So, it is that what just now I have said, cutting force and cutting temperature will be discussed today. And if we go to the next slide, this is a small description of how this cutting force is developed. This force is required for deforming the work material which is ahead of the cutting tool, and the force develops because of the resistance offered by the work material. So, it is the strength of the material makes this growth or development of the cutting force. In the process, we can look into why do we need at all this understanding of this cutting force. So, here we highlight in this slide the purpose of determining the cutting force. Now, obviously, the machine tool cannot work without a prime mover, and in this case it happens to be a motor. So, the power of the motor, how much will be the kilowatt of this one, then definitely one has to know the cutting force into cutting velocity, that gives you an idea of power. So, even for selection of the motor we need the clear idea of the cutting force. Then comes the point number 2, it is design of machine tool and cutting tool. Definitely all the structure of the machines, kinematics, then the structure, bearings, various kinematic elements, all will be strained, and there must be a limit to that straining. So, accordingly we have to have proper design, and there cutting force has a important role to play. Similarly, for the cutting tool, this cutting tool holder should not bend, should not have deformation, or it should not even break. Cutting edge may break if the force is quite high. So, for that also cutting tool geometry size has to be designed. For that we need to know the cutting force. Now comes very important consideration, new work material. A metallurgist can develop a work material for certain application, and he can claim this is better than the previous one. But in that case, machinability is one of the criteria. Unless we can machine it, perhaps it has no such significance in engineering use. So, machinability means with what ease we can machine or what may be the difficulty, immediately cutting force becomes an indicator. By applying our common sense, we understand low force, definitely it is good, machinability, large force, it is a matter of concern. Then comes the tool material, choice of tool material and tool geometry. So, choice of tool material and tool geometry, we can understand that these are also going to influence the cutting force, particularly friction at the chip tool interface or the work flank interface. The cutting force generation is influenced by the rake angle, other geometrical features, then friction definitely at the chip tool interface, that matters. So, we understand that material of the tool and its geometry in combination, they are playing a very important role in deciding the cutting force, and naturally selection should be according to the level of cutting force we like to have or expect. Cutting parameters, we know speed, feet, depth of cut. These are the 3 parameters all of us we know. Cutting velocity has some influence, speed, that is velocity part, then feed and depth of cut directly influencing the cutting force because of the size of the cross section of the uncut layer depends upon these last 2 parameters. Finally comes cutting fluid, particularly if it has this lubricating component, how to reduce the friction and how efficient it is in reducing that chip tool interface friction, that definitely again indicated by the cutting force. So, at least we have all these 4-5 points, the purpose as we have laid down here, that we know why this force should be analyzed and force should be determined either analytically or by some experimentation. Now we go to the next slide. Now friend, it is important in cutting force analysis, theoretical prediction is very important, relevant, and in that case we have to make a modeling of the whole process. Now to simplify the process, we consider it as orthogonal cutting. Yesterday also I have mentioned that when we mean orthogonal cutting, it is a two-dimensional phenomena, chi flows in orthogonal direction, and to have that condition, necessary condition is that lambda should be 0. There are other things, but at least lambda should be 0. Tool should be sharp, it is not a blunt tool, and we should not have large edge rounding radius, then it becomes plowing, it is no more shearing. So problem will have different dimension, then definitely no side flow of chip, that is another condition. So it is a plane strain condition. We consider cutting velocity is constant, uniform all through, and then type of chip means it is a continuous chip with no built up edge. If there is built up edge, you understand friction part is there, but geometry of the tool also keeps on changing, and then you have transfer of the material on the underside of the chip or on the cutting or the finished surface. So these are to be avoided. So these assumptions we have to reasonably accept. We have to create a situation in practice that those assumptions are reasonably accepted. So this is what we mean by orthogonal cutting. However, reminding you that in actual field machining, in industry or in some other application in fabrication, lambda is seldom is equal to 0. Rather, we should provide a negative lambda or a positive lambda depending on the situation, and in that case we cannot consider it as orthogonal cutting. So it is a free cutting and lambda 0. So auxiliary cutting edge does not come in picture and the lambda is 0. Now to give an example of this free cutting, let us have a quick look to this picture. Say this is one cutting tool I have drawn. So this is the direction of feed direction, and here we have to place the workpiece. So workpiece should be like this. It is actually a tube. Tube means here you have a tube. Tube is spinning about this axis, and here you have some thickness of the tube, which I have showing with the dotted line. Now this tool has to be placed here, and in that case you can see this is your cutting tool. So this is the spinning and this is the feed motion. So cutting speed is given, and then you have a feed motion. Only this part of the cutting edge that is engaged in cutting, the top or this side, those are not participating. So it is a case of free cutting with lambda 0, and we call it free orthogonal cutting. So this is how we illustrate free cutting with lambda 0. Now getting back to this, so getting back to this conditions we have laid down. Now let us go to the next one. Then comes friend equilibrium of chip segment. So to illustrate this point, I have to prepare one diagram. Let me quickly prepare this one and immediately we see it. This is a cutting tool, and on this you have the workpiece, and as we have explained yesterday, the shear plane, this is the shear plane, this side is the chip. So this is how we illustrate a cutting action. So tool is moving in this direction, this is velocity, and as usual you can note this is uncut layer thickness, this part is A2 thickness of the chip, and here the tool is tool face. So this is clearance angle alpha O, and this side is gamma O, that already we have covered. So this face of the tool is forcing, pressing this material ahead of the cutting tool, which is having a thickness A1, and after deformation it becomes A2, and the whole shearing is taking place along this line. Along this line this shearing takes place. So, this is shear plane. Now, here we have the force. We have two sets of force. One is exerted by the cutting tool from the tool side, another is exerted from the job side. So, between this the material is undergoing deformation and the force is transmitted through this line. So, this triangular portion is a rigid material through which the force is transmitted, and here we have to have the direction which we have shown by the symbol. Let us go to this quickly here. Okay. So, force R and R dash, R is acting from the tool side, R dash from the workpiece side. So, again going back to this sketch, let us see. So, here you have this is R. So, this you can extend this line of R, and from the workpiece side you have R dash. So, it is R and R dash that is in equilibrium. So, if you like to draw the free body of the chip, you can do like this. First of all, you resolve this force R. So, force R is resolved into two components. One is the normal component, another is the tangential component, which is friction force. Please note down or record the direction of normal force and friction force. This is exerted by the cutting tool. Now, because of R there is R dash, and from R dash also we have two components, but this is acting on the shear plane. So, we can reasonably resolve R dash into two components. One is the normal component, which we denote as Pn, another tangential component Ps. So, under the action of Fn from the tool side and Pn Ps from the workpiece side, the chip is held in equilibrium. So, if I now draw the free body of the chip, it is some sort of this thing. I have separated the chip from the work material from the tool. So, it is free. So, from this side let us put a red line here. So, this is red, this is R dash, and this side through a dotted line, this is the transmissibility of the force. So, this is R. So, from here we have, this is the resolved component. So, N and F, and from this side we have this Pn and Ps. So, this is the free body of the, sorry, it is Ps. Please note down, it is Ps. So, on one side Fn system and on the other side Pn Ps, with that this is under equilibrium. So, now we get back to the slide. Yes. So, force we have noted, chip is moving with a constant velocity, chip is in equilibrium obviously under this R and R dash that we can see from the sketch, and this is in equilibrium. Next would be to show, okay. So, I have just now narrated R means N and F, normal force at the chip tool interface, already I have shown. Frictional force at the chip tool interface, obviously that is there, and then R dash means Ps plus Pn, shear force which directly causes separation of the chip by shearing, that is the Ps, and Pn force acting normal to the shear plane. So, this has been already illustrated in this sketch. Now, we go to the next slide. Now, friend, this is something very interesting. We have noted the force which are acting from two sides, from tool side and from the workpiece side. However, ultimately which is of interest is Ps and maybe F, friction force, but we do not have any recording device or sensor along those directions. So, measurement of those are important component, we cannot measure them. So, what we do reasonably, we choose 3 axes which are according to the machine configuration. Suppose this is the work done in lathe. So, we know what is meant by x direction, y direction and z direction. Yesterday we have discussed. So, feed means x, radial direction means z, and the vertical direction means x means longitudinal direction, radial direction means y, and vertical direction means z. So, we can resolve this r or r dash in two components, which is actually here r is actually your p x plus p y plus p z, but p x plus p y it is also in the combined form as p x. So, ultimately you can resolve this resultant force r, which is acting from the tool side, into three component, one along the direction of velocity, that means in this case the perpendicular direction, along the feed direction, that is feed force, and one which is in the radial direction, that we call the radial thrust force. P x y we call it resultant thrust force, P z means main or tangential component of the cutting force, and P y is the radial component of the cutting force. So, this way we can resolve this thing into three components. So, friend, reminding you that P x, P y, P z, it is to facilitate measurement. However, we have also noted that P z into V c, that gives you the cutting power. So, estimation of the cutting power, you need to know P z, then feed force and into feed velocity, that gives you the feed power. However, feed velocity is marginal compared to the main cutting velocity. So, we can ignore. However, for say design of the bearing, thrust bearing and other thing, we need to know the feed force also, and radial component of the thrust force in the y direction, that is most harmful, most damaging, because in this direction what happens, if I consider, say I like to show you, this is a workpiece and this is the cutting tool, and radial component will be in this direction. Now, in this direction the whole job will be deflected, and this deflection means you cannot ensure accuracy on the job. Depth of cut will keep on changing, and it is held between center or a center and on the left hand side on the with the help of a 3-jaw or 4-jaw chuck. So, rigidity of the whole system will keep on varying as the cutting tool moves from the tailstock side to the headstock side, and you have a deflection pattern, and ultimately what you get, that cannot be a cylindrical surface. So, anyway, we have to keep it in mind that P y component should be as small as possible, or rigidity of the setup is such that in that case the P y cannot make such kind of local elastic deformation, which ultimately lead to an inaccuracy in the job dimension, in particular on the diameter. So, I think this is understandable. So, friend, we go to the next slide. So, here we go to the next slide. So, this part we have already explained, and now we go here. Okay. So, friend, now comes merchant circle diagram. We have seen the tangential component. Just now I have explained this tangential component in line with cutting velocity, that gives you the cutting power. Feed force means it is also used for design of the thrust bearing, and there are other issues. Feed power and P y component, it is very damaging. So, this is one set. You have another set is that PSPN acting from the workpiece side, and you have N and F on the tool side. How to put them together in the form of equation or having some representation, and it was Dr. Merchant, that celebrated researcher in the area of machining. He first gave an scientific treatment of the whole thing, how to put all this force together and correlating that, and that can be represented within a circle, and that is known as the merchant circle diagram, and diameter of that circle, that becomes actually the resultant force R. So, let me try to draw this circle and we can still keep on discussing on this particular subject. So, let us try to draw the circle here. So, this is more or less the circle drawn, and in that circle we have to show this force system. Now, here I place the tool point. So, tool point means the tool should be recognized with the clearance angle and with the rake angle. So, these are the clearance and rake. So, friend, you can immediately recognize the rake angle of the tool. Obviously, that is orthogonal plane. So, this is the tip of the tool, and we assume that on the tip of the tool all these forces are acting. So, here comes, now we should show where is the direction of velocity. Definitely this is the direction of velocity. So, I show this is the direction of velocity. So, this is in line with Pz. So, Pz will be shown by one caudal length and intercept. From this point you draw one line in the direction of velocity, and this chord length shows one force, and that is Pz force. And at right angle to that we have the Pxy force. How do we get it? Let me explain here too. This is the orthogonal direction, and if we consider one cutting tool like this, it is engaged in machining. So, this is the job workpiece that is spinning, and this is the center support, and here perhaps we have a chuck. Okay, it is spinning. So, this is one point I have considered here. So, where is the velocity? Velocity is like this, perpendicular to this plane of the paper. So, it is because it is tangential, and then what we see, Pxy, that thrust force, that is in this direction. Why it is so? Because the chip is emerging out, flowing in this direction, that is the chip flow direction. So, this is Pxy, and Pxy you can resolved into two component. Let me try to show you. This is Px, and if I resolve it, we get two more component. This is Px and that is Py. So, friend, these are the forces acting from the job to the tool on this side, thrust given on the cutting tool. Of course, it is action and reaction. So, Py radial, Px is axial, and tool is also forcing the job in both the direction. In this direction, that is the force exerted by the cutting tool, and in this direction radial, that is also the force exerted by the cutting tool. So, it is a two dimensional what I have drawn, that is in the orthogonal plane. So, Pxy we have to place it. So, placing the Pxy, it is not a problem here. So, I must draw one horizontal line, that is Pxy. Okay. So, we get Px and Py, and if I now join these 2 points, perhaps I can get the diameter of this circle, and this one give you the resultant force which we call R, that is from the tool side. It can be from the other side. So, it is action reaction. Now comes what about F and N, which are exerted by the cutting tool. So, for that what you have to do? You have to extend this rake surface. So, you extend this rake surface and you extend this line. So, you join this line. So, you get another chord length, and normal to that you draw another line. So, it is normal to that. Okay. So, this is diameter, you have one chord and this is along the direction of rake. So, friend, this is actually the friction force which is prevailing at the chip tool interface, and that is the normal force N which is acting normal to this surface. And you know F by N, that is the friction force. So, naturally this F by N means this angle should be eta, friction angle. This is gamma O. What remains to be done in this diagram, and after drawing these lines it will be completed, we have to identify the direction of the shear plane. So, from the lesson what we yesterday covered, we learned, we know how to determine the shear plane angle from the chip thickness rake. There are standard relationship, geometrical relationship. So, from that we get to know how to get the shear plane. So, this shear plane orientation also I have to show here. Say this is your shear plane and orientation. I draw with this. So, this is your shear plane orientation, and shear plane orientation means it is with the direction of velocity. So, this angle becomes beta, and what remains to be done, this, so this is another intercept, and then I join this one. So, this is full set. So, this is another set, means in this case you have PS, you have PN. That means these are the component of the force which are supplied by the cutting tool. Means if we go over here, get back to the previous diagram, getting back, that this R, which is nothing but a combination of F and N, which is transmitted because of the transmissibility, this is supposed to be a rigid body. So, here you get this R, you resolve into two component again, which is equal to PS and PN. It is on the reverse direction because it is supplied by the cutting tool, but as a reaction of the workpiece, that is in the reverse direction. So, finally, what we see here, that this circle which was actually established, set by Professor Marchant. So, it correlates all the forces. That means, if we see here one by one, F and N exerted by the cutting tool, this is your cutting tool, it is orthogonal cutting tool, then PS by PN, these are the force which are acting on the shear plane. And as I have mentioned in my early section of my lecture, that this PS is directly responsible for shearing or separation of the chip. So, it is the PS value and PN is acting on that, and finally, we get PZ, it is the force in line with velocity, direction of velocity, this is the direction of velocity. So, PZ into Vc, that gives you the cutting force, and it is also the way we have, say for measurement sake, we have the dynamometer. So, how these sensors will be oriented? Best thing would be to have the orientation of the sensor along some chosen coordinates which is universal. So, for lathe x, y, z are universal, nobody can change. We have similar coordinate for milling machine, drilling and X-ray machine. So, accordingly, if you place the dynamometer, we can measure Pz, Pxy, and then from Pxy to Px and Py, and from there we should be able to establish a relation between this measured quantity or known quantity and which are to be determined. Okay. So, friend, this is all about Marchant circle diagram, and another thing I make here, this is gamma. So, this is just for you to note, this is gamma O. So, this angle will be eta minus gamma O, this included angle. That means angle between the direction of Pz and the resultant R, that is eta minus gamma O. So, I have shown what is mean by beta, what is mean by eta, what is mean by eta minus gamma. So, this way we can see that this Pxy, Pz, they are connected by eta minus gamma, Pn and Ps, they are connected by eta minus gamma plus beta, and F and N, they are connected by the angle eta. So, that you have to note down. So, we get to the next slide. Okay. So, friend, if you have followed the diagram, merchant circle diagram, which I have drawn in your very presence. So, from there you can have a look that this this r is equal to Pz by cos of eta minus gamma, which is again equal to Ps by cos of eta minus gamma, and which is further equal to n by cos eta, and from there we know that if we know Pz, then we can determine the value of Ps and n, provided we know eta, gamma and beta. So, there are ways how to determine those, but at least if we record Pz, then Ps and Pn can be determined. Further to this, we have one more relation, Pxy by Pz is equal to tan of eta minus gamma, and then F by n is equal to tan eta, which is known as coefficient of friction, but friend, here we should be careful to make a statement. It is actually apparent coefficient of friction, because it is no more in the elastic range. This deformation takes place sliding in the plastic. So, it is our convention to call it apparent coefficient of friction or ratio of tangential force to the normal force. Finally, we arrive here the normal force which is acting on the shear plane, and this shear plane and the tangential plane, these two are connected by tan eta minus gamma. So, please have a look on the sketch what I have made, and then you follow the relation, everything should be very clear to you. And finally, the whole importance of this merchant circle diagram, so significant, so important to all of us who are doing research in the area of machining, for a quick assessment of the situation, whether it is machinability of the work material or performance of the cutting tool or cutting fluid, force reduction, force increase, which is quite critical in that case, that this simple circle with showing all the cutting forces, that is so handy, so useful, that with that you can make a fair assessment of the situation. Okay. Now, we go to the next section. I hope you have realized, understand, you followed the whole thing, understanding is clear. If you have any question, perhaps later on we can discuss on that. Okay. Now, we go to the next section of the slide. Yes. So, followed this. So, friend, we have to go to the next one. So, this is one step. So, now we go to another step. This part already I have shown you. If you have followed the drawing just now, I have completed that Px and Py, these are the two forces, these are the combination of this. Okay, thank you. So, these are the combination of this Px and Py. So, Pxy. Now, it is obvious that this angle is phi, principal cutting edge angle. Now, if this is principal cutting edge angle, you can resolve this thing. So, this will be phi and this will be 90 minus phi. So, if you resolve Pxy into Py, then definitely your Pxy, Py will be is equal to Pxy cos phi, and Px will be equal to Pxy sin phi. Now, from this, what is our conclusion? Our conclusion is that phi has a very important role to play in determining or in monitoring the value of y component and x component of the thrust. So, if this is the case, then we should be careful, we should make a judicious selection of the value of phi when it is very critical. Suppose if it is a slender job, say maybe a slender job like this, what I put it here, and then L is quite large compared to the diameter. So, with little push it will be like a bow shape. So, this is not permitted. So, in that case Py should be very small, and how to make it happen? These two equations give you that answer. Phi should be as large as possible. If you have phi 90 degree, Py component vanishes. So, it is only Px. So, with Px you have thrust on the bearing, but no thrust on the job. Your job is protected, and that part. However, this is only one part of the story. You cannot just keep on increasing the phi. Then in the next section we realize that with increase of phi the temperature also can rise. So, this is also one thing we have to keep it in mind, that value of phi should be chosen in a manner that you can control the cutting temperature, you can control the cutting force, and it is ultimately the performance of the cutting tool, and then the deflection of the job, which is also becomes very crucial. We have to anyway control it. So, according to that we have to apply our judgment to choose the value of phi. Okay. Now, we go to the next slide. So, this is here. Okay, friend. Now comes estimation of the cutting force. So, estimation of the cutting force, you can find that this Pz can be put in the form Pz is equal to tau St into cos of eta minus gamma into sine. How do I get it? Perhaps I can have this treatment here in your presence, so you can appreciate that one. So, the basic equation we have already written, that Pz by cos of eta minus gamma O, that gives you Ps by cos of eta minus gamma O plus beta. Now, from this we get Pz is equal to Ps into cos of eta minus gamma O into cos of eta minus gamma O plus beta. Now, you have to replace Ps. What is meant by Ps? It is a shear force. So, shear force means area under shear into the shear stress, dynamic yield shear stress. Okay. So, how to replace this Ps? Let us see. We put tau S, that means the dynamic yield shear strength of the material, and to have the shear force, perhaps we can get back to one of our drawing just now I have made. So, please have a look here. So, this is actually the length of the shear plane, Okay. Now, if this is the length of the shear plane, how we can express this shear plane length in terms of A1? This is A1. A1 means uncut layer thickness of the thickness of uncut layer. So, this length from this point to this point, length of the shear plane length is given by A1 by sin beta, because this angle is shear angle. So, A1 sin beta. Now, you have to get the width of the shear plane, which happens to be B1. Of course, it is orthogonal cutting. So, we consider B1 is equal to B2. So, consider this as B1, and so shear plane area would be length of the shear plane into width. So, area of the shear plane, if I put AS, which means area of the shear plane, that will be A1 by sin beta into B1. Now, this area has to be brought here in here. here tau s into a s. So, tau s into a s. So, you have to finally replace p z is equal to tau s into a s into cos of eta minus gamma o in divided by cos of eta minus gamma o plus beta. So, from there as a replacement what we get, this is a1 b1 by sin beta into cos of eta minus gamma o divided by cos of eta minus gamma o plus beta. And friend, this is a1 b1, and you see in case of turning, I just try to illustrate this point. So, in this case it is the turning process which is taking place here, and this one is the cutting tool. So, what we can see, just a moment, we show it, this is the axis. So, this side you have one center support, this side also have some center. So, spinning, this is feed S. So, where is the depth of cut? You see, this is the depth of cut, that is T. This angle is phi. Now, where is the width of cut? Friend, depth of cut we understand. What is width of cut? This is actually the width of cut, because that is the chip, flow of chip, that is the flow of chip. So, width of cut. So, obviously from this simple geometry we find this width of cut, which happens to be now B1, B1 is T by sin phi. So, width of cut is T by sin phi, where T is the depth of cut. Now comes the question, what is A1? A1 is actually the thickness of uncut layer in the orthogonal direction. Friend, reminding you that this diagram what I have drawn, that is in orthogonal plane, this one too in the orthogonal plane. So, you have to find out that the tool is moving through an amount s per revolution of the job, that is the feed. So, in one revolution one ring will be deformed and it will come in the form of a chip, one revolution one ring. So, the component of S, that the component of the S in orthogonal direction, that you have to consider as the penetration of the cutting tool. That means, if I make a larger diagram, larger figure. So, this is the cutting edge, and here you have the feed, this is the feed, this is your feed, then this component, this is the feed in this direction, okay, and this is now comes the value phi. So, perpendicular to this is the cutting edge, this one is the cutting edge. So, let us change the color, this is the cutting edge. So, perpendicular to this cutting edge you have to see the advancement of the cutting edge, perpendicular advancement of this penetration of the cutting edge perpendicular to the cutting edge. That means, you have to consider this component, and that is actually the advancement of the cutting edge in the orthogonal direction, and this happens to be S sin phi. So, it comes to that when you put S and you have A1. So, this A1 means here S sin phi. So, you replace this A1 with S sin phi and B1 with T by sin phi, and what you have 1 upon sin beta into cos eta minus gamma o by cos eta minus gamma o plus beta. So, from this we get finally that result, that it is now P z is equal to T s into S and T. This sin phi cancels out, and we are left with cos eta minus gamma o divided by sin beta into cos of eta minus gamma O plus beta. So, this is our final expression, and getting back to So, getting back to we find finally we see this one. Okay. So, thank you. So, we finally arrive here. What I have shown you, you finally have tau s into feet into depth of cut into cos of eta minus gamma O. I have already written those things in the paper, divided by sin beta into cos of eta minus gamma O plus beta, and this is put in the form f. F is a form factor. So, this form factor decides what is the magnitude of the force. So, its thing is not that difficult, it is within our domain, provided we know the value of f, which is a trigonometrical ratio, then it should be possible for us to define or to estimate without doing any experimentation. It is a quite significant work that without doing any experimentation, if you know the shear strength of the material, if you know feed and depth of cut, and knowing the value of f from that shear angle and a relationship, it should be possible to estimate the cutting force without even having a dynamometer. Now, friend, further to this, f is put in this form a minus b gamma plus zeta. Now, a minus b gamma plus zeta, that is a general form of expression for f. Gamma means your rake angle, and in this case it should be gamma O, orthogonal rake, and zeta means chip reduction coefficient, which is known as A2 by A1. So, A2 by A1 gives you the chip reduction coefficient. Now, A and B depends on the boundary conditions. Now, exactly what is meant by this boundary condition? We know that work material varies in terms of its strength, ductility, hardness, brittleness, and so on. So, it is a wide range. So, wide range means I can have cast iron on one side, mild steel on the other side, brittle and ductile. You can have graphite reinforced plastic, or this your fiber reinforced plastic, glass reinforced plastic, PVC, all these things are brittle. Brittle plastic, cast iron, that all, even machining of graphite, say for example. And on the other side you have mild steel. By way of illustration, you have aluminum, copper, all belong to ductile family. So, thing is that the value of A and B, that will depend very much on this property of the material, ductility or the brittleness. Now, here Dr. Marchand, Professor Marchand has an unique work of giving a solution to this problem where things are all unknown. Now, in this case, according to Marchand's first solution, we get n minus gamma plus 2 beta is equal to pi by 2. Now, how do we arrive at that? What is the assumption in that? Let us little discuss on this topic, that it is actually the expression for Pz. What is the expression for Pz? We write it again here, Pz is equal to tau. I have written in the slide tau, but sometimes we also put tau s, means shear strength, but you can write tau, tau into s into t into cos of eta minus gamma O divided by sin beta into cos of eta minus gamma O plus beta. Okay. So, now Pz into Vc, that gives you the cutting power. So, Pz into Vc. Now, the whole idea here is that how to minimize this power requirement or force requirement. Actually, what we find in nature, every material has a path of least resistance to which leading to fracture or failure. Now, this concept has been used, and here we see that under which condition this Pz into Vc means cutting power, and if we separate Vc, then only we are left with Pz. So, when this Pz will be minimum. So, the objective here is to find out from this a pragmatic way of getting an expression which will be very handy to be used. So, here idea is Pz minimum. So, what is done? So, it is actually derivative of Pz with respect to shear angle and put it to 0. If you just do it considering that n does not change, n is constant, and definitely a cutting tool means their gamma O is constant. So, n is constant. So, only it is the beta which may vary. So, from there if you put derivative and put it to 0, from there you arrive at this result that n minus gamma plus 2 beta is equal to pi by 2, and from this relation you finally get Pz is equal to tau s into St, and if you put this thing here in this whole expression, it will be substituted by this term 2 cot beta. So, 2 cot beta into this. So, if you know the value of beta from chip thickness measurement, you can have a fair estimation of that. But interestingly, what we have that this model is not an universal model. This model is only useful for brittle material, and for ductile material it is not useful in that if you make a prediction that gives an underestimation of the force. Suppose you use this relation and try to estimate the force in machining mild steel, which is a ductile material, your estimated value and actual measured value with the help of a dynamometer, you can see dynamometer gives a higher value. So, friend, this is an underestimation of the force, and that is why we cannot use it for this purpose. So, this will be good for brittle material, plastic, cast iron and so. So, Merchant also offered a second solution which is known as eta minus gamma O plus 2 beta is equal to C. So, friend, you please note down that this pi by 2 is replaced by another term C, which has been already displaced in the slide, but since I am doing some work here, I am showing that C is obviously C is less than 90 degree. Had it been 90 degree, we could have got this result. So, this is also one assumption, one consideration, that this tau s, which is a constant for a particular material which has been assumed in this case, that is not true. Actually, what we like to show here, let me get back to this one to save some time. So, friend, here in this diagram, if I recall this diagram, you see here you have Ps component and here is Pn. So, what is Ps? That is actually the shear force arising out of the shear stress, and then you have shear force. But this shear force we assume in this solution, which we have shown that tau s is constant for the material. However, this may not be always true because of presence of this normal force on the shear plane. So, the ideal model is that tau s should not be a constant, it is not a constant. So, it is not equal to a constant, rather in the second consideration what has been said that this tau s can be represented by tau O plus k into sigma n. Now, what is sigma n? Sigma n is the normal stress arising out of this Pn. That means, in summary, if we have the presence of a normal force on the shear plane, then the shear stress will no longer be a constant, and larger the value of sigma n, the actual shear stress will keep on changing, and that is why this universality of this relationship is not valid or it is not accepted. That is why we have a second solution. So, friend, it is just to remind you that this one n minus gamma o plus 2 beta is equal to pi by 2, that is called Marchant first solution, and n minus gamma o plus 2 beta is equal to c, that is called Marchant second solution. And if one can do little bit of the treatment, he can find that this coefficient k is nothing but k is given by actually cot of c. That means cot inverse k is equal to c, and this c is called a machining constant, and it depends upon the material. That means mild steel, low alloy steel, high alloy steel, stainless steel. So, this C value will keep on changing. So, what we learn from this, that if the value of C on the low side, then force requirement will be high. If the value of C is very close to 90, then the force will be on the low end. So, from this we can make an characterization of the work material, and that is what one has to do. So, friend, from the second solution what we get? We get an expression for Pz tangential force, which is given, just you replace, here you have 2 cot beta, isn't tau into S, shear stress into feed into depth of cut into cotangent of shear angle. So, you have 2 cot beta, means cot beta plus cot beta. So, you keep one cot beta here and you replace another cot beta by tan of C minus beta, where C is that value which is given by this relationship, and this C is called a machining constant, which is a characteristic feature of one work material. Okay, friend, this is estimation of Pz. Now, here this is Lee-Schiffer solution. So, it is actually rigid plastic field approach, and from that a relation one can arrive that eta minus gamma o plus beta is equal to pi by 4, and from that using that basic equation means Pz is equal to tau s into St into cos of eta minus gamma o divided by sin beta into cos of eta minus gamma o plus beta. From there, if you put this relationship, if you put this condition, you arrive at 1 plus cot beta. Interesting thing is here that with this result you can get a value which is very close to the experimentally determined value, and this is for mild steel or ductile material. So, for ductile material this relationship would be much more fitting than the relationship given by Marchant solution. However, again if I apply this thing for brittle material, perhaps it could be an overestimation of the force. So, we have seen 3 governing equation with which we can determine or estimate the value of Pz, and with that estimated value of Pz we can do lot of useful work. It can be useful in design of the machine tool, design of the cutting tool, or prediction what should be the power of the motor. So, this assessment just by measuring the beta value and getting this value of Pz, that will be extremely useful in all our treatment work, analytical work. Now, friend, these are the 3 books I have followed as references, that Amitav Ghosh, Ashok Mollik, Manufacturing Science, A.B. Chattopadhyay, Machining and Machine Tools, and A. Bhattacharya, Metal Cutting Theory and Practice. These are the 3 books one can consult to have in-depth understanding of the subject. and it is I mean it should be a companion to those who are studying, who are teaching, who are doing research in this area. So, these are the few reference books I have mentioned, and then I have some questions. So, these questions are very much involving thinking process. So, definitely you can brush up your understanding and knowledge whatever you learn with these questions. Few more questions can be discussed when we get an opportunity, and this is for the first session of our lecture. Okay friend, we come back to the next part of our session, technical session, and this will deal with cutting temperature. So, as we have seen yesterday at the very beginning of our discussion, that outcome of this machining, outcome is chip being produced, and we see the formation of the chip. Then we get a nascent surface. So, on one side, so raw material means raw material is equal to product with definite shape, size, finish and chip. However, it is not out of anything, it is out of something. What is that? Force generation, this is one thing, and rise of temperature, and this force and temperature ultimately leads to some influence on quality of the job workpiece and also on the life, I mean the service life of the cutting tool. Okay. Maybe on 16th we shall discuss on this tool, where tool performance on this, but today now in the remaining time let us have some kind of discussion on this cutting temperature. So, this is session we deal with cutting temperature. Okay, quiz part we have to take care, you have to take care. Okay. So, here cutting temperature. So, friend, first of all it is heat generation during machining. Now, machining is definitely a deformation process. We do lot of experiment by deforming material in material testing laboratory, but this is a deformation whose magnitude and rate are unmatched by any other processes mostly. So, these two things, large magnitude of deformation and a very high rate of deformation, that leads to very large generation of heat, and which will lead to rise of temperature. Now, effect of this consequence. Now, heat source in machining. Let us examine this way. We have the cutting tool, then comes the finish surface, and this is shear plane. You have this side in the form of chip. So, we have to complete this part. So, here as we have said, you have primary shear zone, and then we have a secondary shear zone, that means primary shear zone, that means this slot from this is the primary shear zone, and then chip tool interface. After that it gets lifted. Okay. So, it gets lifted. So, it loses contact. So, up to this point you have, this is what we call chip tool interface, and then if it is an worn tool or deformed tool, now it is a point contact, but this is the machine surface. If it is an worn tool having an wear flat, now this is an worn tool, and if we have an wear flat like this, then this is also become a third source of heat. So, 1, 2 and 3 when it is an worn tool. So, these are the two sources, and you have to have energy balance in that. So, energy balance means, okay. So, heat sources just now I have narrated drawing this sketch, and then we go to the, so effect of temperature, why we should deal with this at all. So, friend, two things just now I have mentioned, it is force and temperature, it is on the product quality and on the performance of the tool. both will be affected. So, we have to pay attention. Now, how this quality of this job is going to be affected? You know, if you do not have uniform temperature, there may be thermal distortion of the job. Then you have oxidation on the job. If it is in open atmosphere, temperature is quite high, it is a virgin surface, it will be immediately attacked. Then the another one step deeper is burning of the job, and it may not be with machining, but with grinding we have seen the gradient is so high that we have even burning of the finished surface. So, oxidation, burning, these are the matter of concern, and we have to pay attention, because surface is just prepared, just formed. It is a virgin surface, absolutely nascent surface. So, attack will be severe. And finally, what is of immediate concern, that is thermal residual tensile stress. Thermal residual tensile stress. So, when we have such kind of material, and we machine it at a very high speed or temperature by some reason very high, then you have to certain depth, you have a temperature profile. It is that called the temperature gradient. Whatever may be, the cooling on the surface will be faster. So, this will try to contract the layer beneath it. So, it is something like that. If we consider a flat surface, so here the cooling will be faster. So, this will try to contract, but that will not be allowed by the layer just beneath it. Same material, it is not two different layer, the layer beneath it, because of this temperature gradient, it will not allow. So, as a result of that, the top layer will be under tension, and that is called residual thermal stress. And why it is harmful? Because we have to conserve the tensile strength of the material. Now, if there is some frozen stress, you can imagine on the stress strain graph that baseline will be shifted. So, you have a baseline, and if this is your curve, then because of this stress already we are here. So, your difference is less. So, naturally this stress that is frozen and that is eaten up because of this thermal gradient and residual frozen stress. So, anyway we have to reduce this effect, and when the material spins at a high speed, whether it is an alternating stress, you can imagine that on the outer layer in each cycle it will be under tension, and that may lead to a fatigue failure, and it is the endurance limit will be less. So, obviously your life cycle will be less. So, these are the few things. It is not only for those who are involved in manufacturing by machining, grinding, but it is also important that after this treatment it is going to be used. It is just not on a machine surface, it is going to be used in making some machine component, say spindle, shaft, some rotary component, and in that case if this surface stress is not properly monitored or conditioned or neutralized, or if we do not induce some compressive stress, then it will be aggravated. So, anyway, in the floor as machining people, those who are involved in machining or machining specialist, one has to take care of this temperature. It should not spoil the quality of job. So, friend, we always talk about finish and accuracy of the job, but this residual stress what we talk about, that is called surface integrity. That means holding the characteristics of the surface during machining. It should not get deteriorated, but rather attempt should be made to improve the surface integrity. That is what we understand, and in that respect that controlling the residual stress is very, very important. Then we go to the slide. Okay. So, friend, on the tool side we have to see rapid tool wear. It is temperature sensitive. You know, tool wear, of course we can discuss in detail, but friend, just one or two line I may add here, that in high speed operation the main problem is rapid rate of tool wear. It is just not rubbing, but it is a temperature sensitive diffusion caused by either chemical reaction or mutual solubility. That means work material becomes the solvent and tool is solute and the material is eaten up, and then there is loss of material, and which means tool wear. So, it is temperature sensitive. Plastic deformation, the tool does not hold the required hardness, it is the retention of the hardness that is very much affected. So, we have no other choice but to see the fate of the tool, that it is undergoing some plastic deformation, that means geometry is totally distorted and it is of not much use, and you have to withdraw the cutting tool. And finally, thermal fatigue. So, whatever I have said, the rapid tool wear that may happen during continuous contact, say high speed turning, continuously chip is flowing. But when it is thermal fatigue, it is like, say take example of interrupted cutting, job may be not regular one, or say best example would be milling cutter. So, it is an interrupted cutting. So, you have a cyclic mechanical loading and also cyclic thermal loading. So, when you put them together, effect is severe and the tool is affected by this thermal fatigue. So, at least we understand that protection of the tool and protection of the job means controlling the temperature. So, friend, purpose of determination of cutting temperature. So, friend, this is just a summary. Friend, ultimately it is machinability, how good the material is being machined or how good the tool is in machining. One is being machined, machinability, another is machining capability. So, both can be judged by this cutting temperature. It may be because of the work material, it may be because of the tool material or tool geometry. So, definitely to survey machinability of new work material, one metallurgist develop a material, but during cutting temperature is so high that it is damaging all the cutting tools. And then comes to evaluate roll of cutting parameter. So, roll of cutting parameters means speed, feed, depth of cut. I may choose certain parameter for in consideration of the productivity or other issues, but finally we find temperature is so high, it is unmanageable and tool is failing so rapidly that the whole purpose is lost. So, this is one thing, and from the tool geometry point of view, friend, this is also very important, that when we talk about the temperature effect on cutting tool, it is the material of the tool, but also the geometry of the tool, means your clearance angle, rake angle, nose radius, and these are the three things which can, if we make an intelligent way of selecting those, definitely we can manage the situation with great success and the tool can perform to your satisfaction, but provided you know the effect of this geometry in controlling the cutting temperature, which geometry increases the cutting temperature, which geometrical feature can reduce the cutting temperature, all this thing an in-depth study becomes very significant. And then obviously cutting fluid and cutting method of application. So, when it is cutting temperature, it is both, it is the energy because of the deformation in the primary shear zone, and also it is the energy spent in the chip tool interface, which is called a secondary shear zone because of the stagnant friction at the chip tool interface, that becomes almost another source of heat. So, how this fluid can at least bring down the temperature considering the friction aspect at the chip tool interface, or overall temperature can be brought down by its cooling effect. So, when it is a cutting fluid, we pay attention to both these things. One is the tribological property, reducing the friction. Another is to bring down the temperature by cooling. So, both the things are there, and one can judge this to capability of the cutting fluid, and net effect should be reduction of temperature. That is the final result. So, we go to the next one. So, friend, temperature in primary shear zone. Now, let us just look into this. I draw this cutting tool. Primary shear zone. This is the chip, and from there it gets lifted. Okay. So, this side machine surface. So, friend, we can see so many lines, flow lines. So, these are the flow lines, and these are the flow lines which has this trajectory like this. And one can be very close to this, which will be in close proximity of the chip tool interface. Now, if we consider one point which is approaching the shear plane, shear zone, there will be immediately a rise of temperature. Now, how do we make assessment of the situation? This Pz into Vc, that is the rate of energy supplied, Pz into Vc, and that has two components. One part you spend in this Ps into Vs into shear plane, and here you know Vs is the shear velocity, Vc is the main cutting velocity, and all are related by this relation Bc by sin cos gamma. So, this way we can find that this is the relation shear velocity, chip velocity, and main flow velocity. So, we can find out here that this one, it is F into Vf. So, this becomes the source of heat in the primary shear zone. So, when this thing approaches, finally you have a shear temperature, shear zone temperature, and which will be given by theta s. I mean the rise of temperature, because you have to consider the ambient. So, I simply consider the rise of temperature of the material which is just crossing this shear zone, and it will be Ps into Vs. However, friend, here we have to put one constant. That constant means it takes care of the heat flux, which again flows back to this main material, that means on the machine surface. That means, so to say, a part of it will flow back, and which is given by this fraction C1, and the 1 minus C1, that will be carried by the chip, it will be transported by the chip in this direction, and here it is rho c into Vc into A1 into B1, that is the basic equation. So, this is volume specific heat, material flow rate, and you can get theta s in this form. Now, here C1, value of C1 to be determined. Now, here two pioneer worked in this area, their name is Weiner and Rapier. They made a solution to this, how you get the value of C1. Now, this C1 value you get by this C1 is equal to given by this 0.7 minus 0.06 into R tan beta. That is the relation, and for that you can consult any textbook. All these things are given there. And what is R? R is actually a thermal number. It is given by rho C V C A1 by K. Rho C is the volume specific heat, V C is the main cutting velocity, A1 is the thickness of this uncut layer, and K is the thermal conductivity. And you can put it here, and what is tan beta? Beta means the shear angle. So, putting those things in this gear, you can get the value of C1, and putting that value C1 here, you can fairly estimate the value of theta s. So, that is your shear zone temperature. However, as it moves, all the points are moving a point very close to this line, that means this level of this uncut layer, no, from the free surface to this depth level. So, a point situated in this level, it will almost come in contact, will be located at the chip tool interface, and as a result of that, this will attain further rise of temperature. So, further rise of temperature is also expected, and to get an idea of this, we have to see how much work is done in the secondary shear zone. In the secondary shear zone, I have already shown F into Vf. So, this is going to be F into Vf. So, it is going to be F into Vf is equal to, we consider it is a rise of temperature, further rise, and we consider this as theta average, and theta average into your rho C into flow rate, means V C A1 B1. So, from there we get theta average is F into Vf by rho C V C A1 B1. So, that is theta average. However, one thing is interesting to know that, so that means the point which is moving, it is already hot with this temperature theta s, there will be further rise. So, total rise will be on an average theta s plus this theta average, that is theta average because of this interfacial action. So, that energy we have considered. However, here we can see that this temperature, it will vary depending upon the conductivity, because it is also known in theory that because of the conductivity, the temperature is never high in this zone, rather temperature is high at a distance away from the cutting edge. So, if you have a temperature plot, you may find that if it is the rake surface, if it is the rake surface of the tool, and this one is the clearance surface, and if we like to show the profile of this temperature on this rake face, it will be something like this. So, highest temperature is little away from the cutting point or the cutting edge, it is because of the rapid conductivity of the heat. So, highest temperature is little away. So, from this point of view, there is further consideration that how to get this. Okay, now perhaps we can little switch over to this. Okay. So, this part already we have taken care of, that whatever is displayed here, that has been already told, this theta s is equal to this, and this is, we call it C dash. I have written here C1. So, better you consider it C dash, because C1 we shall use in another treatment, and rho is called a thermal number, which is rho C V C A1 by K. K is the thermal conductivity, and this is volume specific heat. Now, getting back to this one, yes. So, friend, this is what we get, as I have written already, it is matching that your average temperature will be given by this theta average, which is here we have written as theta f, and this is given by friction force divided by volume specific heat into volume rate of flow. But again, Wiener and Rapier, we can it is again Wiener and Rapier, these are the two names, Wiener and Rapier. They have also proposed that there is a maximum rise of temperature, and this maximum rise of temperature divided by this average one, that is given as 1.13 root over R by LO. That is their treatment. You can see the original work which are referred in any textbook. So, this is R by LO, and this R is nothing but the thermal number already I have defined. And what is LO? LO is, friend, I like to get back to this diagram. This is actually your chip tool contact length. Say it is LC, chip tool contact length, after that it gets separated. So, LC is nothing but LO, this LO is nothing but LC by A2. This is a parameter which has to be the replacement which is replacing this LO. So, LO is LC by A2, and what is A2? A2 is the chip thickness. So, it is the chip thickness and the contact length, or say contact length by chip thickness, that becomes one coefficient and it goes into the root R by LO, and that gives you a maximum temperature. So, finally, what we see, that final rise of temperature, maximum rise would be given by this maximum rise theta max. So, friend, do not confuse with this theta m. This will be the final rise of temperature. This is given by theta s plus theta m. So, this part is the contribution of the primary shear zone, and this is the contribution of the secondary shear zone, and in this way we can get the final temperature, and this is the one temperature one can look into, because this temperature is going to affect the wear on this cutting tool, and this is one of the matter of concern for all those working using this cutting tool. But there is another way of handling this problem. How we can do it? Chip tool interface from dimensional analysis. This was proposed by Merchant and Shaw. So, according to them, we can choose two quantities. I have already written this Q1 and Q2. So, friend, here this is actually CV, means volume specific heat. Volume specific heat means CV, it is not C into V, it is CV, and CV means it is rho into C, rho density and specific heat, that gives volume specific heat, and there we have average interfacial temperature divided by EC. What is EC? EC is, let me write. So, in this case we write Q1. So, it is a dimension, we get two dimensionless quantity. Q1 is rho C, let me write this way, and then it is theta I divided by EC. Theta I means interfacial temperature, this is rho C, and we have another quantity Q2, which is rho C into Vc into A1 by K square. These are the two quantities, these are the two dimensionless quantities. Now, if you plot Q1 against Q2, then one can find out a relation like this C1 into Q2 to the power n. means, or rho c theta I E c is equal to C 1 into rho c V c A 1 by k into to the power 2 n. Okay. When you plot, it has been found by those researchers that k n found out to be very close to 0.25, and if that should be the case, then what we find, rho c, rho into c into theta I divided by E c is equal to C 1 into rho c V c A 1 by k to the power 0.5, and just by transposing what we have, theta I is equal to C 1, a constant, into E c into root over this your V c into A 1 divided by rho c into k. This is, friend, one of the very good indicator of what goes on at the chip tool interface when you change the cutting velocity or the true feed or the feed. And friend, what is E c? E c is the specific cutting energy. So, how do we get specific cutting energy? It is something like that. We have P z into V c divided by, that is the power, rate of energy divided by material removal rate, means V c A 1 B 1. So, in terms with proper unit, it is P z by A 1 B 1, but it is not Newton, it should be joule per meter cube or kilojoule per meter cube. It is the joule, it is the rate, this one is also the rate. So, it becomes joule per unit volume. So, this is E c. So, from this relation we can also get an idea of interfacial temperature, and this one can be very easily experimented to get this line, and from this what we find, that this one, from this what we get a relation, relation means from this we get a relation that theta I and V c, it goes like that, and theta I, it is, and also with A 1, theta I with A 1. A 1 means also in terms of feed, A 1 is equal to nothing but S sin phi in case of turning. So, it is S sin phi, though that also follows this relation, and this is what you achieve experimentally. You independently use a work tool thermocouple, very convenient way to measure the interfacial temperature. It is an average one, and if you measure those things with a properly calibrated work tool thermocouple, you can have a plot like this. Now, this can be supported by this equation where we get an index of 0.5. So, this one and experimental results, they are reasonably matching, and from this we understand the effect of velocity. So, effect of velocity is to increase the temperature, but at the same time if I draw the reference of cutting force, then it is simply P z, and by V c it is falling in nature, it is falling in nature. But so, where is the answer? So, it is falling in nature, P z is falling in nature, but it is not rising in a linear manner. Why the temperature should rise? One thing is that your cutting power, so that is actually P z into V c. P z into V c is the main cutting power. Interesting thing is that if we consider that P z into V c as the main power source, then with this definitely we have a linear rate of increase of the power and linear rate of increase of the temperature, but that does not happen. Why it is so? That with increase of V c, P z is falling. So, this is Pz into Vc, that plot should be also made. So, ideally if one plot Vc versus Pz into Vc, that means which is the cutting power, an interesting correlation one can establish, and that may follow this temperature relationship, because force is falling, it is not a linear drop, but speed is increasing linearly. So, if it would have been that drop in force means the increase in velocity, or so to say, by increasing the velocity we have drop in same proportion, this power should not have increased. So, velocity is increasing, force is falling at the same rate. So, it should be a horizontal line, neither it is a linear one. Because of this, perhaps it can be like this. So, if one plot, perhaps he can get into this insight. So, this is one way of explaining the thing. But when it comes to the depth of cut, when it is the depth of cut, definitely we can see here. So, friend, just now I have mentioned the effect of Vc. Now comes the effect of S, that also I have mentioned, because this A1 means actually S sin phi. So, here both are involved. So, from this what is our conclusion? Our conclusion is that if we take a tool with different phi value, this is one tool, you can have one more tool having this shape. So, this is phi 90, this is phi less than, say this is 60 degree. We can have another tool maybe with say 30 degree, just for explanation. Okay. So, now we have 60 degree. So, friend, one tool with 90 degree phi, second one with 60 degree, and the third one with 30 degree. So, this 30 degree, 60 degree on 9 means what? It is affecting the value of A1. That means, for the same value of feed, A1 is changing. So, when phi is large, A1 is large, and when phi is small, A1 is also small, but your rate of movement or material removal rate does not change. So, if we have phi 90, we expect a large value of the temperature, because we can just have our attention here. This is the value A1, which means actually we should better write here, this is C1 into EC into root over Vc into S sin phi by rho Ck, rho Ck. So, this is final. And another interesting thing, suppose your depth of cut is this amount for this tool, 3 tools with different phi, feed is same feed, and depth of cut is same. So, this is your depth of cut. So, what is our observation? Please have a look. In this case, this is your depth of cut. All the cases depth of cut is this T, but what about the width of cut? This is the width of cut. Here the width of cut is large. Here width of cut is equal to depth of cut. Here width of cut is greater than depth of cut. Here width of cut is still more than what we see here. So, what does it mean physically? Physically means thermodynamic load per unit length of the cutting edge, that also you are reducing. So, indirectly that has an effect in reducing the temperature. So, when we use a small value of phi, definitely we have a better way of controlling the temperature rather than when we have a larger value of phi, and that one should be taken into consideration. And if I increase the depth of cut, say for this one tool, I take just one tool, this is one tool, you keep on increasing, this is depth of cut, then you increase further, then you can further. So, what is the effect? Physically, what does it mean? When it is material removal rate issue, it is Vc into S into T. So, we increase S or T to improve the material removal rate, but if I increase S, definitely I am touching the value of A1, and when it is A1, then getting back to this equation, temperature may rise. But when I increase the depth of cut, you can get higher material removal rate. Thermodynamic load per unit length of the cutting edge remains same, because you have larger section, so you can divide it by the total length. So, per unit length load remains same, mechanical load or thermodynamic load. So, it is said that when it is thermodynamic load, depth of cut has not much role to play, and it is rather safe to increase the depth of cut, provided it is permitted by the dimensional requirement of the work. Finally, we come to this effect of T by S. T by S. So, what is this T by S, friend? Very important, ratio of speed to depth of cut to this is temperature. So, this is the temperature theta I, and if we have T by S, if we increase this, rather we can reduce this cutting temperature. That means we engage larger section of the cutting edge, and thereby thermodynamic load, specific thermodynamic load can be also reduced. So, T by S ratio is also that significant in holding or controlling the cutting temperature. Okay. So, effect of Joule geometry on cutting temperature, obviously I have shown the effect of phi. Now, it is for the effect of gamma. Naturally, what I find, this side effect of gamma rake angle and theta I. Obviously, you can understand that the cutting temperature that is affected by this theta I is equal to C1 into EC into root over Vc A1 by rho C K conductivity. Now, if I reduce the value of Pz, definitely that will influence EC, and then definitely you have a drop. However, we have to keep an attention that too much of reduction increase of positive break, that may weaken the tool. So, this is also one point to remember. Otherwise, if we give a positive break within reasonable limit, within 5, 10, 15 degree, we get immediately a positive effect. Similarly, for alpha, that is also, if we have theta I and alpha, then what we see that if we avoid rubbing, then at some point we can have reduction of this temperature, but if we go further to this, then we avoid rubbing, but if we increase alpha too much, then there will be less mass and then heat transfer will be less efficient. So, we can find that the theta I value again can go up with a low value of alpha. Low at this end, we avoid rubbing, we get a very favorable temperature, but when we go on the other side, mass involved is less and we can have a rising trend. Reference, but I must go to one term what we call cheap equivalent. We have not presented in the slide, I have to write it here, what we call cheap equivalent. Friend, this is also an important criteria, cheap equivalent. That means one tool is in cutting action. So, when it is the cutting action, so here cross sectional area of the chip, that is ST, and what is the contact length. So, this is your contact length. So, at least we have this contact length. So, perimeter of the cutting edge in contact with the job, that length. So, length is the length of contact, it is not the contact length with the chip, it is the length of contact of cutting edge with the job, cutting edge with workpiece. So, there is a term called cheap equivalent. So, Q is the cheap equivalent, this is given by L by ST. So, this is one criteria. If we can keep L by ST as constant, we can keep the face temperature or the tool temperature as constant. If we increase S, similarly proportionally the value of L should be increased either by depth of cut or by radiusing. So, if we have radiusing we get larger contact. So, with this chip equivalent holding the chip equivalent constant, we can also keep the cutting temperature constant. So, this is all about that our presentation, and we go here. So, these are the references. So, you have 4 references including fundamentals of metal machining and machine tool. The other day I have given, it was Boothroyd. So, who has written this book? So, with that we go to the next slide, and here okay, he has time. Okay. So, with that we go to this one. So, friend, here these are the some quiz. So, these are the theta average is proportional to EC, VC or S. It should be proportional to EC, it is not directly proportional to VC and S. Thermal number does not depend on VC, S and T. It does not depend on T, it depends on VC and it depends on S indirectly, because A1 is S sin phi. So, that is the way you can look into that. And maximum temperature rise at chip tool interface does not depend on chip tool contact length or chip thickness or thermal conductivity of the work material. It is actually thermal conductivity of the material. It does not depend on chip tool contact length or chip thickness, but it does not depend on thermal conductivity of the work material, okay, at the chip tool interface. Then fraction of primary heat that goes to the workpiece depend on shear angle, depth of cut or none of this. Primary heat that goes to the angle that depend upon the shear angle, because if you have seen the formula, this is actually, if you have seen that formula, that portion, this is given by 0.7 into 0.06 or tan beta. So, in that case it is the tan beta, that is the shear angle component that comes here, and that is why we call it that dependence of the shear angle with this particular value of this proportion which flows back to the heat workpiece. Now, tool temperature is reduced with increase of gamma, alpha or R. In fact, tool temperature you can reduce quite reasonably with increase of R, because in other case what happens, it is the body of the tool. So, there you need more mass. So, if you increase the value of R, then definitely you have more mass involved and directly you can reduce. But when you increase this too much, then definitely force will rise and you have less mass, and if you have less mass, then definitely you cannot have reduction in temperature. So, to add mass you have to increase the value of R. So, with this definitely we have considered the cutting tool temperature issue and its dependence on this, and that is all about our lecture. And if you have
how to measure the temperature generated in chip tool interface.
Chip tool interface, yes, that interface. Part, yes. So, what was the part first?
How to measure the temperature in chip tool interface?
How does it rise?
How to measure the temperature?
Oh, how to measure it? Okay, friend, this thing can be done rather in a very convenient manner. You have a chip tool thermocouple. So, chip tool thermocouple means here you have this cutting tool and here you have the workpiece. And this workpiece must be insulated from the lathe body. So, if you have this chuck, so the whole thing. So, here please note down, please note, here you must have insulation, this must be insulated, tool should be insulated from the tool post. Here also you have insulation, and as the chip is flowing, let me show you, as the chip is flowing, here you have this contact, this is the contact. So, this becomes one your generator of thermo EMF, it acts like a cell. So, what you have a cold end, cold junction. So, here you can have one carbon brush or copper roller which will roll over it, and then from the tool side. So, this is the chip. So, from the tool side you take one tapping point. So, this one and this one, that should be connected with a millivolt meter. So, as you start working, you get a millivolt reading here, and with that millivolt you can get an idea. However, you have to calibrate this couple. Here it is tool work thermocouple. It is a tool work thermocouple. So, this tool work thermocouple should be calibrated. How can you do that? It is not a very difficult task. You take a long chip and you have this, it is welded to this tool, okay, and then the whole thing you can put in a hot bath. It can be a salt bath, it can be an oil bath, or it can be a lead bath, or if you take enough precaution not to allow any error to creep in, you can hit this zone with a flame, and you have to put one standard thermocouple, that means K type chromel alumel thermocouple side by side. It comes like a probe, it is an inbuilt thermocouple having two. So, you have 1 millivolt here and you have one more millivolt here. So, from this you get the temperature directly because it is already calibrated. So, this reading, if you match it, you get one calibration curve for your work tool thermocouple. This side it will be theta and this side it will be millivolt, and it may be of this side. So, during cutting you get a millivolt reading and you get this temperature. This we frequently we do, and from that definitely you can have 2 curve or 3 curve depending upon the effect of velocity or speed, or even cutting tool material. If you have an lubricating coating, definitely that will have an effect on this temperature. So, friend, this is one work tool thermocouple which can be conveniently used provided you have a extension of this line, because if you have in between hot junction, that will give you a parasitic voltage, okay, error voltage. So, it should be reasonably long. So, this point is the cold junction and this is the hot junction. That is all about. Is that clear to you?
Yes, sir.
Okay. So, you can handle this thing in your laboratory if you like, take using a carbide tool and then having one just like I shown a brush which will be a tapping point, a carbon brush. So, with that, and this will be a copper lead sufficiently long. So, this should be not too hot. So, with that you can have the millivolt reading here. HSS, yes, high speed steel, okay, HSS as cutting tool. So, what is your exact question?
Why is only the HSS as a commonly used cutting tool?
Why HSS is used commonly as a cutting tool?
Yes, sir.
Is it that?
Why you are not going for other material?
No. Okay. Let me repeat to be sure. You have said why HSS is used as common cutting tool. Is that your question?
Yes.
Okay, friend. There are several reasons. Number one, that if you have a low power machine where you cannot attain the high speed, you have to use a positive rake to reduce the force and to reduce vibration. So, that is why you have to use low speed operation, and low speed operation you have to use a tool with positive rake, number one. So, that you get less force with a low speed. Low speed operation with low cutting force means high value of positive rake, number 1. Number 2 is that if you do not attain high cutting speed, then also you have to use high speed steel. What would be such case? You have, say for example, a slender job, 10 millimeter diameter, it is not 100 millimeter diameter. You cannot attain the cutting speed because you cannot have excessive RPM. No, it is not a grinding machine. So, in that case, although the machine is perfect, but you cannot attain the cutting speed. So, you cannot always use other tool which are meant for high speed operation with negative rake. So, there also you have to use HSS. Number 3, when it is a forming tool, you cannot use carbide or ceramic to have that particular shape or form on that. So, these are actually some of those reasons why this HSS tool has to be made, and still it is in use. You cannot 100% discard them. Forming tools, say for example forming tools, grinding of the tools becomes very difficult task with carbide or ceramic. So, if you have a HSS tool, that form you can give there and you can use it rather conveniently. Okay. So, friend, let us summarize. A machine very old, it is vibrating, you cannot attain high speed, and then you have to use a tool with positive rake which can give low level of cutting force. You have no choice to use a carbide tool which are used with negative rake, means large value of force. Now, to offset that large value of force, you have no other option but to go to a very high speed with negative rake. Yesterday I have shown that with negative rake, if you go for any high speed, it is independent of the rake, whether it is 5 degree plus or minus 5 degree. If you have a very high speed operation, this chip reduction coefficient does not depend much on the rake angle. Okay. So, this is one, and then if it is a low power machine, you cannot attain that speed. So, a machine is vibratory, a machine is low power, machine is not rigid, and you have small diameter job, you cannot attain that speed, and finally you have a forming tool where you cannot grind rather easily on carbide or ceramic tool. At least we find 5 points. Alternative to HSS, you mean the alternative to HSS? Is it that your question?
Yes.
Okay. Alternative to HSS, say friend, nowadays this HSS are coated with titanium nitride. HSS are coated with titanium nitride, titanium aluminum nitride. Various coatings are available. So, with those coatings you can go to a very high speed operation, and very high speed operation relatively you can at least double that speed. So, that is one alternative. So, nowadays hardly we use uncoated HSS, but HSS with a coating, and with that coating definitely wear resistance goes up and you can use higher speed. But carbide tools as an alternative, you need a high speed machine, but at the same time I would say that carbide tool of 50 years back and carbide tool as of now, there is a big difference. Nowadays also the carbide cutting tool industry put lot of effort to increase their toughness. So, micro grain, nano crystalline or nano grain carbide. So, with that there have been some attempt to make carbide tool even with positive rake, and in some restricted application those things could be used successfully. So, you have to approach how to increase the toughness of this cemented carbide. That is also another area of research. So, friend, I find a question here, what is the significance of chip thickness? Friend, for one uncut layer, you have one uncut layer, and if chip thickness keeps on increasing, that is not a good sign. What is our simple objective? Objectives to, with what ease we can get the chip out of the parent material. So thickening of chip means large deformation. So that is not a good sign. So chip thickness divided by thickness of the uncut layer, that is the index of machinability. So thicker chip means poor machinability. Friend, how will you calculate and improve the tool life? Friend, when we discuss tool life and tool wear, there we can look into, and improving the tool life means better tool material, we can discuss that day. What parameter influence cutting force more? Cutting velocity, depth of cut, or cutting feed? So friend, cutting force. Now you see, if you look into the basic equation, Pz is equal to how much? Pz is equal to tau s. Tau means shear stress into feed into depth of cut, okay, into a form factor, and this form factor is given by cos beta minus gamma divided by sin beta into cos eta minus gamma plus beta. Okay. Now this form factor will be influenced by the cutting velocity. So you can find from that equation, this equation. Friend, this is the equation. So this is the equation, we have already deduced this thing. So deduced, so this factor, this finally decides, you have tau, you have feed, depth of cut. So directly you increase twofold, force will increase twofold. But this factor, this is a hidden parameter. Who is working behind it? It is actually the cutting velocity. Cutting velocity has two roles. One is, as you increase the cutting velocity, the shear zone temperature, you recall theta s, that will come down and that temperature will rise. So rise of temperature means fall of the strength. So the strength will fall, that is in positive way working velocity. And another thing, that with increase of velocity, this this friction angle also comes down. Coefficient of friction, that also falls, and that is why this form factor also favorably decreases. So answer would be that this has direct influence, but speed also has one influence in reducing the force. One way, by reducing the strength of the material through increase of shear zone temperature, and on the other hand it touches this friction angle, friction gets reduced. And if you see this equation, basic equation, very interesting and important, reduce this eta, then this beta value is also increasing. It means chip thickness is also falling. So chip thickness decreases. So our conclusion is directly S and T will proportionally increase. Vc also reduces the force by increase of temperature, and finally it will become a saturated curve. So let us have this thing here. If you call Pz, so with S it goes proportionally, because that is equation. But when it is Pz by Vc, Pz and Vc, it drops down and it becomes saturated, because below that you have no further decrease in the coefficient of friction. So that it is almost approaching like a fluid. Chip becomes almost like a fluid, it is almost like a fluid friction, that means a fluid flow past the wreck surface. So that is your saturation point, and after that chip will become molten, it will melt. Thank you so much. Have a nice evening.